A lot of the current problems with lithium-ion batteries come down to the electrolyte. The electrolyte is the reason why we can't have higher voltages, why batteries are degrading, and why batteries are so flammable. But the electrolyte has to do a lot of different things, and it's really hard to do all of them at once. So I was super curious as to what are the different kinds of electrolytes and what sorts of trade-offs do we have to make. First off, what even is an electrolyte and why do we need it? Well, basically the way a battery works is it's shuffling electrons between two terminals, the positive one and the negative one. And when we are moving those electrons, we can basically harness their movement as electricity, because that's really all electricity is, the movement of electrons. But since we're basically moving these charged particles back and forth, we now need some way to balance out that charge difference that we're creating. And since we're moving negative things back and forth, we need to also move positive things back and forth, or positively charged ions. So the electrolyte is basically a medium solution that sits in between the two battery terminals, and it lets the positive things, so the ions, move between the two terminals to balance out this charge difference that we're creating by moving the electrons. So electrolytes need to conduct ions quickly, obviously. They also need to be electrically insulating, because if they weren't, then we would be directly connecting the two terminals of the battery, which would be short-circuiting it, which is not great. And the third thing the electrolytes need to do is they need to be stable within the high voltage environment that is a battery. And they also need to be stable against the positive and negative terminals of the materials that they've made. Before we move on, there are a few ideas that we need to get at an intuitive level. So the first is that when these ions are moving through the medium, they're not moving alone. They're surrounded by other things, and how tightly they're surrounded determines how fast they can move, unless the things surrounding them are able to rearrange quickly. The second thing is that when we have current flow, it's not just one type of ion moving. All of the charged species are going to move. So even though we call them lithium-ion batteries, it's not just the lithium ions that are moving. Any kind of ion is going to move. And if other types of ions move more easily than the lithium, then those other types of ions are going to end up carrying more of the current. So we'll get back to those things by the end of this video. But for now, let's look at the three types. So first up, we have liquid electrolytes, the one that we've been using for nearly everywhere. Let's look at liquids through three questions: how the lithium is surrounded or coordinated, how it moves, and then what are the limitations with this kind of electrolyte. So in liquids, lithium is coordinated by solvent molecules. So you can think of this as like a celebrity moving through a crowd and then being surrounded by bodyguards. The solvent molecules move with the liquid, and that's actually what makes it much faster than the other types of electrolytes that we'll get to in a bit. It's not hopping, it's just kind of flowing. And this is called vehicular diffusion. So this type of diffusion is modeled by something called the Einstein-Stokes model, which basically says that the speed is dependent on the viscosity of the solvent, not necessarily the charge on the ion. So basically, how fast it moves is going to depend on how many other things it's carrying with it and how willing that solution is to let something flow through it. So basically, higher viscosity plus more things attached to it, so more things that it's being surrounded by, would equal slower. And theoretically, decreasing the viscosity would help, but practically you can't really do that, because then that would cause other stability issues with the battery, which we don't really want. I wanted to add some notes about the downsides of liquids. So they're usually made of organic solids, which means lots of carbon, hydrogen, and oxygen. And these were chosen because they dissolve lithium well. They're manufacturable at scale. They have a wide operating temperature range, and they wet the electrodes well. So an electrode, it's kind of like a sponge texture. It's got a lot of pores in it. So because this is liquid, it can get into all those pores and therefore have super great contact with the electrode. But because we're using organic solvents, that makes the electrolyte very flammable, which is not good. These electrolytes are electrochemically unstable. So the carbonate groups, which means a carbon-oxygen bond, those have an operating voltage range of about 1 to 4 volts, but batteries typically operate at 2.4 to 4.2 volts. So we sometimes end up operating outside of the voltage range. And then also, there is like, one of the biggest things in batteries is increasing energy density, and higher voltage would directly increase energy density. So ideally we would increase the voltage, but right now we're being limited by the electrolyte. So basically, this battery is thermodynamically unstable. It would want to react spontaneously, and that's spontaneous reactions are usually a fair bit dangerous. But basically the way that we make this work is because we're basically forming this film that kinetically stabilizes the battery. So when you have the electrolyte and the electrode right beside each other, they'll react and they'll form these decomposition products that will then like form this little tiny film between the two, and then that film is going to prevent electron transfer, so it's going to prevent them from reacting. Liquid electrolytes are cheap, practical, and used almost everywhere today, but voltage limitations and then also flammability are making people look more towards solid state alternatives, which we're going to get into next. Now, the same questions, but for polymer electrolytes. So a polymer is basically a chain of repeating units. You can think of it like beads on a necklace. And basically, in polymer electrolytes, the ions only move when the polymer chains move. So basically, you have your polymer chain, the ion is sat at, it's like bonded to one spot on the polymer, and when that chain moves, the ion gets the chance to become closer to another spot that it could hop to. So in this case, instead of like flowing like liquid, it's hopping, and this makes polymers, this makes the ion conductivity worse because it's not continuous. So polymers top out at around times 10 to the negative 4 Siemens, which is the standard unit for measuring rate of ion diffusion. But a liquid electrolyte can get to times 10 to the negative 2. So literally orders of magnitude better. Another thing that really matters for polymers is something called the glass transition temperature, or TG. So this is basically the temperature at which the polymer chains will start to like move past each other. And this is the point where the polymer chains become flexible and we can actually have that ion hopping occur. So below this temperature, polymers are really not very conductive at all. So logically, you might think like, let's just lower the glass transition temperature. But if you do that, you're compromising on mechanical stiffness, because glass transition temperature is basically the point at which the chains start to like slide past each other. But if the chains are sliding past each other, then you have a super soft material. And another thing that the electrolyte, that we ideally want the electrolyte to do, like liquid electrolytes don't do this, but it would be great if they did, is help prevent dendrites. So dendrites are basically like when you get lithium like plating on one of the electrodes, it will like accumulate and it'll like grow this dendrite, and that can eventually cause a short circuit. So we ideally want the electrolyte to be like mechanically robust enough that it can stop the growth. There are a couple of models people use to model this polymer diffusion. One of them is called the VTF, or the Vogel-Talman-Fulcher model, and it's basically saying that the activation energy required for the ions to move through the polymer changes with temperature, because the how flexible the chains are depends on temperature. Another model is called the dynamic perchloration model. So basically, like the old model was called static perchloration, and it's basically saying like, if you have like a grid, it's like random as to if a site is conductive or insulating. So it's kind of like a tic-tac-toe board, and if it's conductive, then the ion will actually flow, and if insulating won't. But this doesn't really work for polymers because the grid is like constantly moving. It's not just a static grid. So this 1988 paper proposed a new model where the grid was actually changing, and that would affect the probability of the ion actually conducting or not conducting. The main idea is basically that the ions can only move as fast as the polymer chains can rearrange, and how fast the chains rearrange depends on temperature. Another thing though about polymers, most of what I've been talking about has been about amorphous. So since polymers are just these long chains, there's like different ways they can organize into being an actual solid. So the amorphous one is basically like if you just like jump everything up like spaghetti. It's just very random. There's like a bunch of empty space. That's really easy for polymers to move through because there is that empty space. So there's like, it's easier for the polymer chains to wiggle, which makes the ions have an easier time moving through it. But sometimes in polymers you get these crystalline regions where the chains are like stacked super tightly, and there's not a lot of free space, and that makes it really hard for the ions to move, because then the polymer chains will wiggle even less. So these crystalline regions are kind of like obstacles for ions. People are putting effort into figuring out how to reduce the amount of crystalline regions that we have. And one thing that they do is called cross-linking, which is like if you have the two chains here, you add bonds between the two chains so they cannot slide like this. This does help with preventing crystallinity, and it also helps by increasing the mechanical stiffness of the thing, but it also increases the glass transition temperature, which we don't exactly want. So there's a bit of a vicious cycle here, and that's prime example of what makes electrolytes so hard. Now for the third type, inorganics. So here, lithium is coordinated by a crystal lattice. So basically, an inorganic is a crystal structure that's got like this repeating grid, and lithium just hops from site to site inside that grid. How fast it can hop is dependent on how big the gaps are, like in between the grids, and then it's also dependent on the activation energy. So the activation energy is like the energy required for the lithium to actually make that jump into the new spot, and that's determined by the crystal lattice itself. This is the static proportion model that I was describing earlier. Liquids are limited by viscosity, polymers are limited by polymer dynamics, and then inorganics are limited by activation energy, like crystal activation energy. So in the best cases, these inorganics can reach similar conductivities to liquid actually, so times 10 to the negative 2, which is pretty good. And how they do it is they basically rely on controlled like disorder inside these crystals. So basically like defects, modified lattices, vacancies, which are like empty spaces that actually let the ions move through this lattice. But it's really hard to get all of those things without like destroying the mechanical and chemical properties of the lattice. Another big challenge with inorganics is the interfaces. So if you remember, I said that a liquid electrolyte is really good at getting into all the like nooks and crannies of the electrolyte. Well, here you have like there's a really hard solid against this really hard solid, and like any kind of gap level is going to be like pretty bad. And the other thing is that these are really hard to manufacture. They're very sensitive to like water and air, so you have to keep them like super sterile. They have to be very pure because any impurities would cause like the lithium ions to just get stuck. And then they're also very brittle, so they're very easy to like crack and everything. So to kind of like summarize these three different types of electrolytes, liquids let lithium move by like swimming. Polymers let lithium move by like hopping kind of across like maybe moving rocks. And then inorganics let lithium move by like subway channels, but sometimes the subway channels don't necessarily line up. Underneath all of that, there are two ideas that explain almost every single trade-off that we've talked about. The first is coordination number. How many atoms/molecules are bound to a given lithium? The way lithium is coordinated controls how easily it can move. If there's strong coordination, then lithium becomes very stable, but it moves slower. And if there's weak coordination, then lithium might be able to move faster, but it's also less stable. But one thing I want to point out here, highly conductive electrolytes don't necessarily have weak coordination. They're just able to exchange coordination very quickly. So for example, they might like, in the example of liquid, it might be like surrounded by a bunch of atoms, and then like it get passed on to a new bunch, and then it just moves through the chain that way. So in liquids, we have dynamic coordination, or very easy rearrangement. In polymers, the coordination rearranges only when the chains move. And in inorganics, we have no coordination rearrangement because the lattice is fixed. The second idea is transference number. So even though we call these lithium-ion batteries, lithium ions are not the only one doing the moving, and sometimes they're not even the one doing the most moving. The lithium-ion transference number tells us the fraction of the current that's being carried by the lithium ions compared to the other ions inside of the battery. A transference number of 1 means that only a lithium is moving, and a transference number of 0 means that no lithium is moving. And usual electrolytes only have a transference number about 0.2 to 0.4. So the reason why this happens is because if lithium is tightly coordinated, then it moves much slower, and the anions might actually move much faster, which means that they will tend to carry more of the current. And when anions are the ones carrying the current instead of lithium, then lithium is going to build up in some regions, and this is going to cause like maybe some of the degradation that causes battery aging. It will cause concentration gradients, and it's generally not like great. We would prefer the transference number to be higher. In liquids, the transference number is fairly low, and it's because the other anions are mobile as well. In polymers, it can be slightly higher, but the overall motion is still very slow. In inorganics, it's close to 1 because the lithium ions are the only thing that can move. So technically, inorganics solve the transference problem, but they introduce a bunch of other problems like mechanical and manufacturing ones, and also the dependence on activation energy. When you zoom out, a lot of the biggest challenges in batteries come down to the electrolyte. Things like voltage, aging, and safety, they're all dependent on the electrolyte. And some of the core principles of electrolyte are transference number and coordination number, which the first one controls how lithium moves, and the second one controls if the lithium is actually even doing the moving. Most electrolyte research today is about letting lithium move easily, safely, stably, and actually carrying the current without paying for it somewhere else.